enough time to discuss all of this. I will be discussing an application involving nanolaminates. I will be discussing an application involving thin film transistor, and consequently a transparent conducting oxide, solar cell, and supercapacitors. But along the way, I'll give you a flavor of of all these various types of applications. Okay, so let me just start with the more esoteric application. This is just to show you how indispensable ALD is in microelectronics. Of course, this type of research is very, very expensive. So this is something that we probably should not be thinking about. But this is just to illustrate how why ALD was developed, why is it important, okay? And there was, as with anything else, if you want to develop something, if you want to propose a research, you've got to justify why you want to do that research, right? And here, so you've got to be able to define the need that you're going to address. Okay? And ALD just did just that. There is this need in the semiconductor industry for a technique that will allow you to code device structures with that are three-dimensional. Because as you know, right now, the limit with which you can miniaturize devices we're getting there. Okay, so they have to think of different ways of inserting more devices into a small area of, let's say, the silicon chip. Okay, and the way you do that is basically the semiconductor industry evolved from a planar structure. In other words, you're making devices just flat, and so instead of making them flat, what they did is to make them taller. Okay, so lower footprint, but basically the same. Basically the same, let's say, channel length. Excuse my. Okay, so that's the idea: is to make this vertical device structures. It can be transistor, it can be for memories and things like that. But as a consequence of that, you need something that you need a way to be able to coat metal electrodes. You need to coat dielectric materials on this vertical structures, and there's no other way to do this except atomic layer deposition. And that was the driver in the electronics industry, to develop this technique. Without this, you won't, Intel, for instance, will not be able to fabricate devices like this. Okay? And the history of this really boils down to going from, these are called nodes. In other words, nodes are just the smallest size features in the device that can be fabricated with standard lithography. So you're going from 90 nanometer to the 22 nanometer nodes. Okay? But in this case, you start to go to, there's been a lot of materials that were required to go from one technology to this technology. One is the development, for example, in the early days of semiconductors, silicon dioxide was the dielectric material of choice because it's very easy, because you already have silicon, so it's a lot easier to oxidize those materials. But then as you go to these lower size features, it was imperative to develop different types of dielectrics, so the so-called high dielectric function materials. And then eventually, in this gate, you have to develop a capability to code conformally. And ALD in all of these processes has been very useful in enabling the IC manufacturing technology to go from that size to this size. Okay. Now, let me, so that's in the microelectronics. Now let me discuss something that is doable, and I think Ian is actually doing some of this work on wide bandgap semiconductors. Okay, so as I said, silicon has been the workhorse for the semiconductor industry. It's got one disadvantage. It's not an optical material. You cannot use silicon for, let's say, making lasers or light-emitting diodes and things like that. Now, also because of the band gap of silicon, which is 1.1, it's not very good for really high-power applications. Okay? So that's why there's an interest with materials that are called wide band gap. In other words, materials band gap is a lot larger than silicon, germanium, or gallium arsenide. So among the most popular ones are silicon carbide, zinc oxide, gallium nitride, and dynamite. Okay. Now gallium nitride is a driver for this very high efficiency light emitting diodes that are used nowadays, especially for lighting. So there's already a history of applications of wide bandgap semiconductors in the industry. And why wide bandgap? Well, I just enumerated here the advantages of using wide bandgap semiconductors. So you can reduce energy losses, higher frequency, temperature, and voltage operation, and lighting efficiency. And these are going to be very useful in, let's say, for example, designing high-speed variable frequency industrial motors, okay? Or high-frequency, high-power density electronics for satellites and radars, for example. Okay? Now, the one that I'm really interested with are the last two. One is for developing power electronics, high-power electronics for inverters to convert. Because remember, if you have a solar panel, right, its output is DC. You have to be able to convert that to AC for us to be able to use it with our everyday appliances. Right? So you have to design these circuits called inverters. Okay? And if you have wide bandgap semiconductors that you can use to make devices out of, then you can have this high power inverters that are a lot more efficient than silicon-based electronics. And then transparent electronics. What do you mean by transparent electronics? Electronics that you're not able to see. Right? So why is this useful? Well, in the US, since I was funded by DOD, that's very useful, right? But also in the realm of consumer electronics, this is really very useful. Well, the more popular examples of this would be Google Glass, or let's say, for example, when you go to Las Vegas every year, there's a consumer electronics show where they show window. Literally, I saw a demonstration. So it will be, I'm sure in a few years it will be in a market where you have a window like this, right? And then you flick a switch, it turns on a blind, okay? Flick a switch, you can see the internet. But if you don't click anything, it still functions as a window. Okay, you still have that same window. But transparent electronics allows you to increase the functionality of that, of that window. So the other thing that you could think of, for example, is, we always want, with solar cells, we want to harvest the visible part of the spectrum from sunlight, right? But there's also the infrared and the UV part of the spectrum. So imagine now that you have a solar cell that harvests the UV and the infrared part of the spectrum. These are wavelengths that you don't see. Okay, so you have a window that is transparent. It's still letting sunlight in, but at the same time it's harvesting, this part of the solar spectrum. Okay, so that's another application of transparent electronics. Okay, so let me just discuss. So this is our own work on zinc oxide. So, well, as I said, my interest with zinc oxide is because it's a wide bandgap semiconductor. Now, what I wanted to do is to be able to also control that bandgap, make it even wider. Okay? And you do that by doping it with magnesium. In other words, you replace some of the zinc with magnesium. But there are certain applications where I want that to be carried out at low temperature. Zinc magnesium oxides by no means a new material. There are other ways of making this. Okay, but I would like to do this using an ALD because of certain specific applications that will require an ALD, right? And the way you do this is really very, very simple. So how do you incorporate magnesium in zinc oxide? So essentially, what you do is, again, using the ALD process for depositing zinc oxide, that's summarized here essentially. You define a certain number of layers of zinc oxide, atomic layers of zinc oxide, okay? And then after that predefined number of layers, insert one layer of magnesium, okay? And you repeat that depending on how thick you want the film to be, okay? And by adjusting the number of zinc oxide layers, you're able to adjust the magnesium content. And you're able to dope the zinc oxide with magnesium. You're able to do this at low temperature. And you're able to do this without any post-annealing or thermal treatment. And you're able to tune the bandgap again. Okay? How do we know that? Well, part of the things that you'll need in any materials development is to be able to characterize the materials. Okay? You want to know, is the hypothesis, is your impression, is what you think you're doing is actually what's happening, right? In other words, here, and here, this one I still don't understand because this is done at 150 C, okay? Normally when you dope a material, let's say you have a zinc oxide, you want to replace zinc with magnesium, you substitute, you literally remove zinc and replace that with magnesium, right? That takes a lot of energy. If you just calculate that, for the chemist, right? But this one, it's a lot more than 150 C, that's for sure. Okay? But here, we're doing this at 150 C, right? And so the question is, are you really able to dope it? And the answer is yes, okay? And these are the evidence for that. One is a technique called X-ray photoelectron spectroscopy. So essentially, you just bombard your material with X-ray radiation, okay, of a specific wavelength, and you look at the energies of the electrons that you knock out of the material. And based on that, and from knowledge of the structure of these materials, you'll be able to identify what's inside the material. Okay? And that's what we've done here. So we're able to, these are all the atomic transitions associated with the zinc and the magnesium. And depending on the relative strength of the magnesium and zinc transition peaks, we can get an estimate of how much magnesium has been incorporated into the zinc lattice, right? And so, that's what we have. So now we have a measure of how much magnesium we have. The other one is now optical absorption. This is something that you have here, right? This is just ordinary UV visible absorption that allows you to directly measure the band gap. And so remember, our aim is to be able to tune the band gap, right? And that's exactly what is happening here. This is pure zinc oxide, this is pure magnesium, and these are in between. You can see how the threshold for absorption, changes as you go from pure zinc to pure magnesium. We can also probe the structure of these films, and again, without going into any details, we're able to see, crystal structures associated with zinc oxide and magnesium oxide, and some in between. Okay, so the bottom line is that with ALD, we're able to synthesize at low temperature zinc magnesium oxide and have the capability of tuning the band. Okay, so what is it? Well, this is just a summary of all the physical properties that we've measured for those different films. So, as I said, one of the things that we're interested in is transparent electronics, right? So this is just a demonstration of a zinc oxide-based thin film transistor that's fabricated essentially by ALD. Okay? So you start with a commercial glass that's coated with a conducting oxide called indium tin oxide. You pattern that by photolithography to pattern the source, gate, and drain electrodes. And then you use ALD to deposit the dielectric, the aluminum oxide, do another patterning. And then once you've done that, deposit another ALD grown conducting oxide, the aluminum doped zinc oxide. And then you pattern that, and then you put the zinc oxide, which serves as the channel, the conducting channel for this device. And as you can see, it works just like what you would expect. Field tunable, gate tunable transistor, and it's transparent. This is the actual device itself. All right. And with this is going to be the basic building block for a lot of things, like for RF devices, inverters, logic gates, photonics. Okay. So photonics covers a lot of things. Anything that uses light is called photonics in this case. So again, I'm not gonna, if I'm going to discuss details on this one, I have to come back, right, to do this for a few weeks. But at any rate, this is just illustrating to you what what ALD is capable of enabling in terms of photonic technology. The basic thing is the what's called photonic crystal structures. In other words, these are really just devices where you have materials in some periodic fashion with different indices of refraction, essentially. Okay? And depending on the geometry, depending on the indices of refraction, you can control the passage of light in these materials. One such example would be, let's say, resonators like this. In other words, this is just a photoluminescence that's coming from quantum dots, and that is passed through a photonic crystal structure, and that transmits light at specific wavelengths. Now, this is also very useful. Let's say, for example, for sensors, right? So you can imagine, let's say that you have this photonic crystal where that passes light at a certain wavelength. Okay. Now, and then you put that in a biological environment, and biological molecules attach on the surface. That's going to change the index of refraction of this photonic crystal, and then once you put that in the light, you won't see anything. So that allows you to sense, what specific molecule you can have. So you can imagine a whole different ways of utilizing that effect, right, to detect molecules, for example, or chemicals, or anything, that changes the index of refraction. Now, there's one thing that I'd like to discuss that's, again, this is along the lines of my interest in energy harvesting. So this one, we always want to harvest energy from the sun, right? But, heat is always with us. Probably not in Baguio, but if you go to Manila, you have a lot of energy to harvest, right? It's very hot. Okay. So harvesting, background heat is it's going to be very useful, especially if you're not thinking about powering houses, but if you're just thinking about powering small-scale electronics that they don't really consume a lot of power. Thermal harvesting energy from just the surrounding heat is really very useful. And as you know, heat, they are at a certain temperature, let's say 300 Kelvin. They correspond to a black body radiation, right? So an example of that is illustrated here. This dashed line here is just the theoretical spectrum for an object that emits thermal energy at 300 Kelvin. Now, what you would like to do is to use photonics to be able to absorb this. Okay? And the way you do this is you do what's just a stack of dielectric metal layers. Okay? And you can actually calculate this one. So these are, in this particular experiment that we did, it uses barium fluoride and nickel chromium alloy to produce, and that's this is one unit, and that's repeated over so many units, and you can calculate the absorption of that particular structure. So in this case, for example, it's we have a calculation of the absorption. If we have 10 periods of this and 2 periods of this structure. Okay. Now, the solid lines are actual data that were measured from real devices that were fabricated. Okay. Now, as you can see, the actual data is nowhere near the theoretical calculation that is expected for these structures. And why was that? Well, the problem is that when we made this structure, we didn't use ALD. It was just use ordinary thermal evaporation. turns out that the roughness of these layers is critical, because if you have a very rough surface, it's on the order of the the wavelength of the photons, then the coherence is lost, and that's why you don't see what you expect to see. Okay, and so what we did was now to use ALD. Okay, problem is that we don't want to put fluorine in our system, so instead of using iron fluoride, we use aluminum oxide. Using aluminum oxide that's grown by ALD, you can see this is comparison of the theoretical and the measured measured structure. As you can see, there's a really very good agreement between fluorine and so the bottom line is that ALD, because of its capability to control the deposition and the atomic scale, really led to the deposition of very good smooth films, and which was critical in making this black body absorber. Energy harvesting. Okay, I'll just discuss a couple of things. One is solar cells, and the other one is capacitor application. Now, there are a whole host of applications related to solar cells, and I just summarized some of them here. Like, for example, it's ALD is used as a surface passivation layer in silicon solar cells. It's used for encapsulation and buffer layers in the CIGS solar cells. In the field that I'm working, we use it for encapsulating organic photovoltaic devices. In addition to that, we also use it for, because one interest that we have is to make this onto plastic. Okay? And so if you're going to make this onto plastic and you want to put electrodes, you cannot do this at very, very high temperature. But the only way you can do that is with an ALD. Okay? And again, also on dye-sensitized solar cells. Now, in addition to this, it's also used as the active absorber. ALD grown materials are also used as the the thin film absorbing, light absorbing layers. In this case, it's an example of an ALD solar cell device that was made with copper oxide and zinc oxide heterojunction. The devices are not yet, they're not yet very good. The efficiency, the highest efficiency that's been obtained is about 2.6%. The other one that's relatively promising material is tin sulfide, again grown by ALD. And these are just summary of the optimization of the characteristics of the material to get the best possible efficiency. And so far here, the best efficiency that they reported in this paper is 2.9%. I just came from a conference in Japan on ALD, and the group who previously reported this were there as well, and they reported efficiencies of about 4.2%. So once you're reaching 5%, then it can be commercializable depending on the cost of producing that. But it's good enough to power low power electronics. Now, in dye-sensitized solar cells, again, this one here, what you want is to make a three-dimensional structure for use as an electrode in dye-sensitized solar cells or even in capacitors. Okay? So one such one is called, making an inverse opal structure. And what it is really is something really very simple. Even this can be done as an undergraduate research.